change based upon the units? And the answer is no. Like if you use different set of units, the structure of mechanics doesn't change. Interestingly, if you use different units for electromagnetism, the structure changes. So, you know, for reasons of, I guess, being forced to, we're going to be using SI, although SI is not the best set of units to categorize electrostatics or electromagnetism. Really, the best set of units are called Gaussian units because it takes a very kind of elegant form. But let me pull up the PowerPoint and just kind of go through this with you guys. So we'll start off with the nature of electric charge. And we've gone through all of these demonstrations. Yes?
Should we just, should we write any notes on this as well?
Not really. I would just pay attention at this point. So, you know, the nature of electric charge we've already gone through. There is a means of inducing or getting something to be charged. There's a few different ways to do it. One way is via what's called the triboelectric effect, which last year I just said it was charging by friction. This year you have the more formal name. Another one is by inducing a charge. And the third one is by conducting a charge. And what is the distinction between the triboelectric effect and conduction? See if you guys can actually distinguish the two. What is the difference between those two effects? Conduction doesn't require actually the friction mechanism. In other words, you just go and conduct charge. And it's via contact, but it's not the type of contact in which basically the force of friction strips one material of electrons. So, you know basically the structure of matter at this point. You've all had a course in chemistry, and to some degree it was covered last year in physics. You know, if you have any type of, generally speaking, well, at least as far as we know, matter basically comes in neutral forms. In other words, if you go and you take just straight up carbon, what do you see? I mean, what do you see from if you were to actually go and do an electrical experiment with it? It's neutral, right? That it requires some type of mechanism to charge it. So what does that imply? That implies that if there are these things that, if there are these kind of elementary particles that make up matter, then they're going to come in equal forms. In other words, the number of positive charges must equal the number of negative charges. Why? Because when we observe matter, like this keychain or any key on here or any of the plastic, generally speaking, it's neutral. So, in addition to that, so as you can see, the very nature of those particles basically facilitates the movement or the transfer of one particular particle, namely that of the electron. And what's the reasoning for why the electron is the particle that gets exchanged? Yes? Correct. It has the least mass. By what order of magnitude? What's a lot? It's about 1,800. So in other words, the mass of a proton is about 1,800 times the mass of an electron. So in other words, what type of force would be required to move a proton 1,800 times the force that would be required to move an electron? So if you apply the same type of force on both particles, what are you going to observe? Yeah. Exactly. It's going to accelerate much greater with a much greater magnitude. So all this is the kind of trivial stuff that is not so trivial when you actually start digging into it. But it's going to take time for you guys to dig into it. You have to go through several physics courses. Conservation of charge. This is not an obvious one. In other words, it's not obvious that this quantity called charge should be a conserved quantity. One of the things that, anybody get a chance to view any of the videos, the Yale OpenCourseWare videos on my Haiku page? If you do get a chance, I mean, at some point in your lifetime, you should watch them. Maybe not this year, but sometime, because the guy who actually is lecturing is awesome. He is awesome. Ramamurti Shankar. He's written one of the seminal books on quantum mechanics. He's a professor at Yale, and those lectures are amazing. And one of the things he actually spends a lot of time on in the first lecture is the idea that all electrons and all protons are identical. And that's kind of interesting. In other words, like, you take any two protons that exist in the universe, and they're completely identical. Right? Is there anything that says that they should be identical? I mean, if you think about how weird this is. You take any two manufactured objects. Are they going to be completely identical? No. Yet, every single elementary particle is manufactured in a completely identical way. That's interesting. So, charge is a conserved quantity. And not only is charge a conserved quantity, but the universe behaves in such a way that charge is quantized. So what does that mean? It's what? Anyone else? What is quantization? Correct. What a quantized quantity is that it only comes in discrete chunks, finite discrete chunks. And what is the smallest chunk of charge? The charge of an electron. So this is one of those classic questions that gets asked in an exam. You're given, let's say, a charge of an electron. And anybody remember off the top of their head what the charge of an electron is? You shouldn't. Don't even want to look it up.
6.67 times 10.
It's close. You're thinking of the gravitational constant. Yeah, 6.67 times 10 to the negative 11th is G. So this is the charge of a single electron. And so one of the classic questions you'll be given at some point in your lifetime is, you're given something like this. I don't know, 5. You find out that some collection of charges has the following charge. And the question is that possible? That's not possible. That's right. This is not a possible type of charge, because that would require having 3 and a little bit of an electron. So it only comes in quantized charges. And now think about, how would you actually discover that? How do you discover the fact that it comes in quantized charges? Yeah, and so this is the Millikan experiment, and it's kind of brilliant. The Millikan experiment was a really, really brilliant experiment, and I actually think we have the apparatus here, but I haven't gotten it to work.
I remember seeing it last year.
Yeah, and basically what he did. And it's a little bit more complex than how I'm going to explain it. But basically what he did, it's somewhere in here. Oh, it looks like this is it. Yeah, milk. This is at least one piece of it. It is a very cool experiment. So let me actually pull up the picture on YouTube, on Wikipedia. So let me see, Millikan oil drop. So here's the apparatus, and it's really worth looking at this thing kind of in detail. So as you see, it requires a microscope. And so what he does is he actually goes and he has this spray of, and what's that spray consist of? It consists of oil droplets. So what's going to happen with the oil droplets when you put them in an electric field? That's a good question. So now, the question is oil a conductor? Yes or no? Oh, I don't think so. All right, so you think it's an insulator, right?
So is that like a thing? It's not a conductor, it's definitely insulator. It's not like...
Well, let's ask ourselves, is that a thing? If it's not a conductor, it's an insulator. Yes or no? Yeah, so you have this two. Is water a conductor? Well, the answer is it depends upon the situation. Pure water is actually not a conductor, but pretty much any water that you're going to get is a conductor. And so the answer to this question is that no, there is no dichotomy between a conductor and an insulator. That actually there's a spectrum. And that if you put, let's say, a true conductor, like a metal, in an electric field, what's going to happen? What's going to happen?
It's going to accelerate towards the... Well, pick up. Wait, it's electric...
Be careful. What is an electric field? Let's actually go through this.
Like positive here, negative here, like uniform.
All right, so now, how can I construct an electric field? That's an extreme version. I can take a single point particle, and let's take a single positive charge. Not yet. A single positive charge. Is that going to create an electric field? Yes. And what type of field is that going to create? What type? Where is the field going to be directed? Away from it, radially outward. That's right. So what's going to happen when you put a metal in that electric field? So in other words, you're not touching that positive charge. You put a metal in that field, what's going to happen? All of the electrons are going to be correct. They're going to all accelerate towards as near to that positive charge as they can get on that metal. Right? So what's going to happen is it's going to be polarized. And as a result of it being polarized, the negative particles, or the overall object, is going to do what? Accelerate. Yes?
I basically reading last night, but I kind of didn't understand what it means to be like polarized.
Okay, so what it means to be polarized is precisely...
Like positive and negative charge.
That means... So here, I'll just draw this out. You have this positive Q. Ah! So here's this Q. Right? And so you know that it's going to emanate an electric field. Right? So now you put, let's say, a conducting strip, meaning this is a piece of aluminum. Right? Is that aluminum? Everyone's Yeah. There you go. So what's going to happen? What's going to happen with that aluminum? That's right. This thing is uncharged, but the electrons are going to be the ones that are free to move, and so the electrons are going to pile up on the left side, which means that the right side is going to be positive. And what's going to happen as a result of that? Well, this is polarized. This is what it means to be polarized.
The electrons charged, or the electrons, like the force on the electrons.
Why? Exactly. So the force on the electrons is going to be greater than the force on the positive ions because those electrons are closer. And so as a result, this whole thing is going to accelerate towards that positive charge. No, magnets are totally different.
Like with the relative getting the charge on the one side and going the other.
Nope.
Magnets are so weird.
Yeah, you'll see. You'll see what a magnet is at some point in this course.
I just have like a general math question.
Shoot.
Like, is the difference in those forces, are they going to get, like, is the difference going to get greater or smaller as it gets closer?
It should. That's a very good question. That's a damn good question. So,
So, the closer would have the greater effect, because the farther it is, the bigger, because it's squared.
Yeah, say it's
The
D,
farther
but it's 1 over D
would
squared.
have less kind of an effect. It'll have less of a charge, so it would be getting divided by a bigger number. So the closer, the like,
yes, I think.
it would still increase.
I think it would increase as you get closer. The difference would increase because that difference, despite the fact they're a fixed distance away, the fact that it's a 1 over that squared, as that squared goes to 0, that force is going to jack up to infinity. That's a very, very, very good, insightful question. You should try to actually show it. So this is the phenomenon of polarization. And the question is can this be done with an insulator? Yes or no?
Would it be harder?
And the answer is it would be harder. And like the classic example is the comb and like pieces of paper. And I don't think that I'll tell you right now, I don't think I'm pulling this off. I do not think I'm pulling this off. So
Isn't an insulator just something that resists more than a conductor, but it's still a
well, which is the insulator here?
It's just like in general.
Well, right now, do you know what I'm going to do?
Are you gonna like
I'm going to comb my hair,
create
right? And then I'm going to. That's right. So let's see if this works. I don't think I'm going to pull this off. Not in this weather, man. It's so humid outside. You got it. You see it, right?
Oh, yeah. You got that one bad boy on top.
Ah.
Oh, that one dropped.
Well, I don't know if it's being blown. Nah. Yeah, I don't think it's going to happen.
We saw it working. Is there a reason why you're touching the paper?
Well, I want to try to polarize it.
No, I mean like before you combed your hair when you're like pressing it.
No, I'm just trying to
Yeah.
make sure they're neutral. So you can see, like, there is something, but it's not strong enough to pick it up. Why? Because of the humidity. That's why it's just terrible to do this in this type of climate. Although, maybe I could do it with something else. Van de Graaff. Well, I could use the Van de Graaff. So, what would I need to take a look? What would I need to do with the Van de Graaff? Where are you going to look?
Where are you going to look?
Take a look at the triboelectric series and see what I just did with my hair and the comb.
Hey, Bruce.
No, first, let's look at human hair is positive, negative, right? So
So the comb had the electrons.
right? So then, therefore,
Paper is slightly positive.
I would want, so this was negative,
Yeah.
so that means I need to take which piece of this? The grounded piece, that's right. So let's see if I can do this.
Jacking up the power.
All right. And someone plug this in.
I mean, pretty powerful.
Yeah. No, I can't. It's just so humid out here. But
I think you got more with your hair. Yeah. Because of that.
yeah, what I'm wondering is,
Just left that sitting. That metal piece.
could you kill it, turn it off? Now, like, give me 1 second, Zach. Cause, all right, now try it.
Oh, that one.
So, as you can see, this is all repelled. Well, there, maybe, there. Get over here! All right. You can kill it. So, yes.
So if you just left that metal piece that originally was grounded, that's not building up the charge, right? It only, like,
That metal piece that's grounded, it's going to build up the charge, but in this room, forget about it. It's going to build up a charge, but that it's just going to leak. So, and in fact, see those edges? They're going to leak better than this. Why?
surface area.
That's right. So in other words, this is why lightning rods work. This is why you put a lightning rod on top of a building. What's going to happen? It's going to continuously leak the excess charge buildup or the charge differential buildup.
Like surface area. Oh, because it's skinny.
It's skinny, exactly. So what I want to show you, first there's electric field, and I will get back to Coulomb's law, or the details of Coulomb's law, in a second. What I want to talk to you guys is about field lines. So, and this is kind of totally new material for you. So, what are field lines?
It's like a visualization of the charge.
So, in other words, it's going to be the line of force acting on the charge test particle. So, first, does everybody have an understanding what electric field is? What is the electric field? Let's actually go over this before I jump ahead. What is the electric field? So if you have, let's say, a charge configuration, right? And I wanted to know the net force of these charges on a test charge. Well, does it need to be positive?
Usually it
Does it need to be? And the answer is no, it doesn't need to be. But this is actually, in other words, the fact that the test charge is positive doesn't affect the overall physics. If it was negative, what would happen? It would just the direction would just flip. So the whole notion of a field is to remove the underlying thing that's measuring the force. So in other words, if you're looking at, let's say, gravitational fields, the gravitational field is what any object put near the Earth, or the Earth's gravitational field, is what any object near the Earth would feel, right? And notice, in the case of a gravitational field, what is that independent of? The mass of the test object. In the case of an electric field, it's independent of the charge of the test object. So what that means physically is that E is defined as the force acting on a test charge, right, divided by the test charge. And in the case of discrete sets of charges, what is the force acting on a test charge? Yenmin. Yes, like for instance, this charge configuration of 4 charges. How would this affect some test charge Q0?
Can you do like almost center the mass with those 4?
Yes, but we'll get there. Yes. What would that force be on Q0? No, I'm asking you to actually outline Coulomb's law here. Yes. Okay, but now we have to be a little careful. So it's going to be the sum of K Q0 Qi over what? Which R? So let's call it Ri 0 squared. And what direction is it? It's independent of a coordinate system. What direction is that force? So for instance, what is the direction of the force of the Q1 on Q0? It is the line that extends from Q1 to Q0. And that's called so this is R hat 1, 0, or more generally, in the case of I 0. So what does this mean? Let's actually go and take a very simple example. So in a simple example, if you have, let's say, 3 charges, or 1, 2, Q. And let's call this positive Q. Let's call this negative Q. And this is Q1. And this is Q2. Okay? Let's write out Coulomb's law. And what I mean by writing out Coulomb's law, I mean actually just doing an FBD on Q0. So where is the force of Q1 on Q0 directed? Which way? That way. This is going to be directed this way. So this is F of 1 on 0. Where's the force of Q2 on 0? That way. So this is f of 2 on 0. Now let's see if this is consistent. So now, f of 2 on 0 is equal to what? It's equal to k times q0 times, what's q2? Negative q, right, over that distance squared. Let's just make these equidistant. Let's call this little r. Let's call this little r. So it's little r squared. All right. And in what direction is it? It's in the, so where is q2 to q0 hat directed? Where is the position vector that extends from q2 to q0 directed? It's directed, not the angle, the position, the unit position vector. It's directed this way. In other words, if I were to ask you the position vector, if I put, let's say, the origin here, where is the position of q0 relative to that origin? It's in that direction. So therefore, this is r hat 2, 0. So notice the force is directed in which direction? In negative r hat 2, 0. Where is negative r hat 2, 0? Towards q2. So everybody got this. This is an important. So this is equal to k q0 times q, right? Or you could say the absolute value of negative q times negative r hat 2, 0 over r squared.
We're saying, for instance, that we have two negative q as like that's the origin that line where they are, so we're going to.
The position vector is always directed from whatever charge Ri to your test charge.
Yeah.
So in the case of the position vector that extends from q2 to q0, that's going this way.
That's negative.
That's positive. That's positive r hat. When I look at Coulomb's law, the actual statement of Coulomb's law, this is Coulomb's law. Now, one of the things I'm trying to show here is that this is completely equivalent to how you guys did it last year. Do you guys remember how you actually found the net force last year? You took the absolute value of the charges and you accounted for direction based on the free body diagram. But the point I'm making here is this. When you go into your next physics course, this is the starting point. You no longer deal with this absolute values. So it's important for you guys to understand how they're equivalent, because you're going to be dealing straight up with vectors. Notice in the case of r f of 1, 0, where is r hat 1, 0 directed? Hyunmin. That's right. It's directed this way. So notice you get k q0 times positive q times r hat 1, 0 over that r squared. Notice in this case, this is a positive charge. So this is also equal to k q0 times the absolute value of positive q over r squared r hat 1, 0. And so what this shows you is that this is going to give you, this is going to be completely equivalent to the following. net force is equal to net K absolute value of Qi, Q0 over R squared, I0, right? And then, see, direction is FBD. And it might be worth actually doing this in one dimension, going through a full one-dimensional example like I did last year. I don't know if you guys remember this. I think I did it in your class, but maybe not your class. Because it was one of those things where one class had more time, they got a slightly different treatment than the other class. So, to illustrate this, what I'm going to do is 1, 2, 3. And just for simplicity, I'm going to make all the distances the same. So here's Q0, here's Q1, here's Q2. I'm going to make this negative Q, and I'm going to make this positive Q.
Oh, is this where we're discharge to make it?
No, this isn't quite that. This is actually to really hammer home the actual Coulomb definition of Coulomb's law, or what Coulomb's law says. So, okay, so which one do you want to deal with first? Force of Q1 on Q0?
Yeah.
All right, so let's say they're all separated by little r. Okay, where is r hat 1, 0 directed? So r hat 1, 0 is directed that way. What is the length of r hat 1, 0? Let's see if you guys remember this. What's the length of r hat 1, 0? What is that called? A unit vector. It's 1. And it's not 1 meter, it's just 1. A unit vector has length 1. And all it does is it's telling you direction.
Wait, you made that unit vector, right?
No, this is Coulomb's law. This is Coulomb's law.
A unit vector, isn't that when like, you take something and divide by its magnitude?
Correct. When you take a vector, r, and you divide it by the magnitude of r. So that way, all it's telling you is its direction. And remember, if you want to multiply, if you want to preserve the value of anything, you multiply it by what number? 1. Hence the unit vector. So what it does is it gives this scalar quantity a direction without changing its magnitude. So r hat 1, 0 is directed to the right. Where's r hat 2, 0 directed? To the, excuse me, r hat 1, 0 is directed to the right. R hat 2, 0 is directed to the, really? Yeah, to the right. Wait, to the, r hat, that's right, r hat 2, 0 is directed to the right. That's right. So they're in the same direction. Should I put Q0 in between them to illustrate this? Just leave it. Okay. So that means these guys are in the same direction. So therefore, the net force on Q0 is equal to K times positive Q times Q0 over 2, that'd be R squared. Good. Yep. r squared in what direction? And r hat 1, 0 plus k negative q, q0 over 2r squared in what direction? R hat 2, 0. But what does R hat 2, 0 equal? They're the same. So this is R hat 2, 0 equals R hat 1, 0. So what I'm going to do, I'm going to, since they're both equal, guess what I'm going to set them equal to? I'll just call that R hat. And to really simplify matters, which coordinate system would actually make this as simple as possible? One in which I set my origin where? At Q2. Very good. And which direction am I calling positive? To the right. So this coordinate system makes the most sense. And I'll call that the r hat direction. So there you go. And so this becomes, instead of r hat 1, 0, just becomes r hat. So this is the proper way of dealing with electric forces. And this is, you deal with electric forces this way, it will serve you well all the way through grad school. Yes?
I still didn't catch why both the R1 and R2 are acting on the same direction.
Because R1 is the vector that points starting from Q1 to Q0. And it's going to be the vector that extends from Q2. R is the vector that extends from Q2 to Q0. R has the direction of that vector. Correct. So let's go through the next example, just so we hammer this home. And so in this case, I'm going to put the charge in between. Damn it. So now, what do we know? R hat 1, 0 is directed in which direction? To the right. R hat 2, 0 is directed to the left. So what can you say? They're opposite each other, therefore R hat. That's right. And so now what we have to do is pick a direction. So pick a coordinate system. So where do you want to put the origin? I'm going to put the origin at Q0. I'd do it at Q1 still. So this is what I'd call positive R hat. Yes?
Are we always presenting that Q1 and Q2 is always fixed?
For these illustrations, yes. Because what Yenman's bringing up is a very interesting point. It's a really interesting question is what you're really asking. And what he's really asking is it possible to construct a stable configuration of charges? I want to talk to each other. Can you construct a sequence of charges such that if you let them go, nothing would happen?
Oh, like
The net force on any of them would be 0?
Mr. Coulomb, are you talking about like those two are pinned to the wall?
These are all pinned to the wall.
No, but what he's talking about.
Yeah, what he asked was, are you assuming that they're all pinned to the wall? And I said yes. And the question is, is it possible that you can not pin any collection of charges? I'm talking about any collection of charges.
I think it's possible.
You think it's possible?
I think you have like, kind of like that setup, like let's say a positive, you have other cards in the middle, but because it's supposed to be equal and opposite.
These have to be strong.
But if nothing happened,
Yes, this is correct.
The only one I can think of is an infinite.
Yeah, these are really.
So you need an infinite set of charges to have a stable charge configuration?
That's the only one that I can think of right now.
And the answer, interestingly enough, is no. It's not possible to create a stable, where the electrostatic force is the only force that holds a charge configuration together. It's not possible.
Even if you put like, oh, I was saying something I just thought. Okay, I'm sorry.
It's okay.
So you put a positive and a positive here, and in between them you put a negative charge. We have the positives on the other side to be greater than the negative in the middle. These two will repel each other, but
Mhm.
because the negative is closer, it's going to have a greater force on the two positives that will attract them.
Correct.
Are there values to keep those stationary like that?
There's no way you can actually...
If they're equally distant and like,
Yeah.
if it's like 4, 4, and 1,
Uh-huh.
and it's like positive, positive, negative, then this one would feel nothing. It would cancel out with these two.
Be careful. The middle one would feel nothing. But the ones on the ends...
But wouldn't the positive one, so you have a positive here, you have Q, like, negative Q level, 0.
Uh-huh.
And then that's like 1. And then you have positive 4 Q.
Uh-huh.
And then the distance are equal.
Yes?
Feel nothing.
No.
Why not? The forces on them would be the same.
What would happen is if the third one felt nothing, right, then the other two would feel something.
Wait, can we do like a free body diagram on it?
Sure. I mean, let's deal with this first, and then we'll go to that question. I'm telling you, it's not possible. You have to nail them.
Is the infinite configuration considered possible or just not?
That's
It's not a physically realistic situation. So, which is why, by the way, this is called electrostatics. The idea here is that, it's one of the reasons why, is that you're dealing with static charges that don't really move. So, all right, so where were we? So, made coordinate system, and r hat is in which direction? It's in r hat 1, 0, correct? So therefore, this is equal to negative r hat, and r hat 1, 0 is equal to positive r hat. And so there you go. From here on, it's just routine. So the force on Q0 is going to be K times Q0 over r squared in the positive r hat direction. All right. Plus K times negative Q0 over r squared in the negative r hat direction. And so what do you notice here? Yes? Do they cancel out? Be careful. They add together. And let's go to the free body diagram to verify it.
Oh, so for this, you're not putting it in absolute value.
No, I am actually being as formal as possible. This whole formulation is the formal view of Coulomb's law. In other words, like,
Since it was out, and even though they were in the same direction, because it's negative, would they cancel out in the previous one?
correct. But in this one, they don't cancel out.
They don't cancel out, they add up.
Correct. So I want to see if correct. So they're additive. So I want to see if they give you. Did your textbook give you this formulation? No, they didn't. They get.
I'm sorry. I tried reading it and I just don't get everything that he was saying. Like, couldn't they just say that?
Yeah, I've done.
No, this is not in your textbook.
Parts in the book.
So I want to show you what this looks like in a higher level textbook. Give me 1 second. All right, guys, so tomorrow, one second. I want to make sure I show this to you. Ah! All right, 1 second. So as you can see, in a more formal textbook, this is how it's defined. So,
For the website, is it on the first 2 readings and like the 3 package, or like?
Pretty much.
I didn't go through all of it. I just like saw like the first like question.
the first set is more of a review.
That's what I saw. I saw that. I didn't.
Later.
What do you think? Hey, how else do you think, okay?
Talk about this next time. I'm just so confused to why it wouldn't work. Because like if you do the math for this one, these two are gonna cancel out. Do the math for this one.
They're not going to cancel out
Why wouldn't they?
because. So let's take a look.
I did it that time.
This is positive 4Q. This is negative. This is positive 4Q. Let me show it. Give it to me later.
All right.
Because I have to prepare for these guys. Shoot.
What days are you available?
Tuesdays.
Okay, thank you.
No problem. All right. Could you guys take that overhead? Where did we leave off yesterday?
Can I use the restroom really quickly?
Don't ask. Just go.